All right, ladies and gentlemen, today we're going to be talking about vapor pressure. And first here, we'd like to go ahead and have a look at a manometer system in which we have a volatile solvent present in a closed-end manometer. Now, if you recall from earlier in our year here, we can look at the presence of those liquid phase water molecules, and due to random molecular motion in the liquid phase, the water molecules themselves, upon jostling one of their neighbors, can escape from the liquid phase into the gas phase, according to an equation here in which H2O in the liquid phase becomes H2O in the gas phase. And the net effect of that is that water molecules from the liquid phase can enter into the gas phase. And as that occurs, the bowl within our manometer becomes saturated with water molecules. Now, those water molecules in the gas phase, as they're in the gas phase, the more there are present there, can collide with the surface of the liquid and recombine into the liquid phase. And therefore, this represents a reversible chemical reaction, physical change, which means that the forward and reverse reaction rates will become equal to each other, and the system will establish equilibrium. Because those molecules in the gas phase are moving randomly, they will be therefore colliding with the surfaces of everything around them, including the surface of the liquid mercury inside of our manometer, and that would imply, therefore, that the system establishes equilibrium at a particular pressure. And we can measure that pressure, which we call the vapor pressure of the solution. Now, the vapor pressure of that solution is dependent upon, in essence, the tendency of those molecules to escape from the liquid phase and enter into the gas phase. That is, the more likely the liquid phase molecules are to evaporate, the higher the vapor pressure would actually be when the system establishes equilibrium. We see this in the real world because we see that molecules of some liquids, like say acetone, which is nail polish remover, have a tendency to evaporate almost instantaneously due to the weak attractive forces between those molecules. Acetone, when spilled on the countertop, evaporates readily, it would therefore be expected to have a high vapor pressure as a liquid. That's in contrast to something like, say, vegetable oil. Vegetable oil, which when spilled on the countertop, would take a very, very long time to evaporate. You could be waiting for weeks and weeks and weeks on end to see any change in the amount of the substance noticed. Now, vapor pressure itself can change for a particular species because we can change the rate of evaporation. Given that this process is an endothermic process, we would expect to see the addition of heat to the system. If we say we're to heat up our liquid, to increase the rate of the forward reaction, that is, the rate of evaporation would increase. And therefore, we expect to see more and more molecules in the liquid phase enter into the gas phase, which would therefore cause a corresponding increase in the vapor pressure of the system. So that is to say that vapor pressure tends to have a positive correlation between temperature and the vapor pressure of a liquid. Now, this is not a unit in which we are studying solely gas chemistry. We are looking really in this unit at solubility chemistry. And so the question I have for you is, what would happen to the vapor pressure of this system if we were to take our solution and dissolve a non-volatile solute into the liquid? Here's where we have to have a moment to have a conversation about some English language here. The word volatility, in a chemistry sense, literally means the tendency of a liquid phase species to evaporate into the gas phase. So as we just discussed, acetone, nail polish remover, would therefore be a highly volatile liquid. That is something that evaporates very, very readily. Something like vegetable oil would be a low volatility liquid. But what we're looking at is specifically a non-volatile solute. And a great example of a non-volatile solute would be something like, say, table salt, NaCl. You can spill table salt on the countertop, and you can be waiting for years and years and years before you see any of it noticeably actually evaporate. So in this process, we're going to go ahead and dissolve a non-volatile solute into our solution. what I want to look at is what is the effect on the vapor pressure of the solution. Now, to understand that, I want to kind of draw a particle picture here and zoom in on the very surface of that liquid. And originally, in a pure solvent here, if this is just pure water, for example, let's say, and all those water molecules exist here in our liquid phase. And because the system has established equilibrium, that implies the rate at which the water molecules are evaporating due to their random molecular motion, giving them enough kinetic energy to escape from the attractive forces which hold them into the liquid phase. That rate of evaporation is exactly balanced by the rate of condensation. That is, again, the system has established equilibrium. And what happens now when we dissolve a non-volatile solute into the solution? You might recall that upon dissolving, a species like salt will disassociate into its component ions, that being, in this instance, sodium ions and chloride ions. So whereas before, this entire solution had been made up of water molecules here, now all of a sudden we have non-volatile sodium ions and non-volatile chloride ions occupying some of the positions within our solution. And the net effect of this is to notice here that if you decrease the number of water molecules at the surface, that should therefore decrease the rate of the forward reaction. That is to say, the rate of evaporation at which water molecules are leaving the surface is slowed because water molecules below the sodium ions do not have the ability to escape into the gas phase. They're essentially blocked by the sodium ions or chloride ions at the surface. So the net effect of that is, for a system that had been originally in equilibrium, we now see a system in which the rate of our forward reaction, that was the rate at which H2O evaporates into the liquid phase, from the liquid phase into the gas phase, is now slower than the rate at which H2O in the gas phase changes back into a liquid. So we do that, it's not forward. So what we now see is a system in which we originally had established equilibrium between liquid phase water and gas phase water. But now, because the rate of our forward reaction, that is the rate of evaporation, has decreased, we expect to see a change in the equilibrium position of our system. And the key idea to understand here is that although the rate of evaporation has decreased, the rate at which water molecules can return from the gas phase into the liquid phase is unaffected because a gas phase molecule can still be attached to the surface because it doesn't need to get past a sodium ion or a chloride ion to become part of the liquid. It essentially becomes the surface itself. So in essence, the net effect here is to decrease the rate of evaporation while maintaining the same rate of condensation. Therefore, we should expect to see a net shift in equilibrium to the left. And upon shifting this equilibrium to the left, that implies fewer molecules should therefore exist in the gas phase when the system has now established equilibrium. And therefore, our rates of evaporation and rates of condensation will reestablish themselves as equal, just however now at a slower overall rate in both the forward and reverse directions. Now, the net effect of this on the vapor pressure is to say that if there's fewer gas phase molecules, we would expect to see fewer collisions, and therefore the vapor pressure of our system should decrease in comparison to what it was originally. The big takeaway from this entire discussion is the net effect of dissolving a non-volatile solute into a solution is to lower the overall vapor pressure of the solution. Now that tells us a little bit about how vapor pressure is affected here. The real trick is now, what effect does that have on measurable properties that we've seen previously of these solutions? And the first thing we're going to have a look at here is the effect on the boiling point of that solution. You may recall from our previous conversations that boiling point is defined at which the point at which the liquid and gas phase of a system exist in equilibrium. Now, another way of looking at that is that if we have described boiling point as being essentially the equilibrium point between those two systems, I want to look at boiling point from a perspective of vapor pressure. Because as we discussed before, we have those water molecules escaping into the gas phase due to their random molecular motion. But at the same time, we have another factor influencing our system here, which is the atmospheric pressure. And that atmospheric pressure, in essence, is pushing downwards on the surface of that liquid, holding it down more or less into the liquid phase. And so another way of looking at boiling point would be the point at which the vapor pressure of a liquid is exactly equal to the atmospheric pressure in in the atmosphere. That is to say, the molecule's tendency to escape from the liquid phase into the gas phase is exactly balanced by the pressure holding them down, and therefore, in essence, the molecules themselves become the atmosphere. That is, they have an equal ability to escape into the atmosphere as the atmosphere has an ability to hold down the surface of the liquid. And it gives us a definition then of boiling point. That is to say that the boiling point of a liquid is defined as the temperature at which the vapor pressure of that liquid is exactly equal to the atmospheric pressure outside. And so our big question now is, what effect, therefore, does the addition of a non-volatile solute dissolved into the solution have on that vapor pressure, and therefore on the boiling point of the solution? So if we imagine that we have originally a solution which we've measured its boiling point, again, that boiling point would be defined as the point at which the vapor pressure of the solution is exactly equal to the atmospheric pressure pushing down on the outside. So if we have an open tube manometer now, and we have some molecules that are in equilibrium with the liquid below them in the gas phase, we could increase the vapor pressure of that solution by increasing the temperature, that is, by heating the system up. So if we add some heat to this system here, that would increase the rate of evaporation. Therefore, more molecules would enter into the gas phase. And as more and more of those molecules entered into the gas phase, in essence, the vapor pressure would increase until the point where that vapor pressure inside equaled the atmospheric pressure outside, and therefore this system would reach boiling. Now let's see what the net effect of this would be on our solution in which we have dissolved a non-volatile solute into the solution. As we mentioned before, the net effect of dissolving a non-volatile solute was to lower the vapor pressure of our solution. So at a particular temperature, we'd expect to see fewer molecules escaping into the gas phase. Now remember that we've defined the boiling point of the solution as the temperature at which the atmospheric pressure is equal to the vapor pressure of our liquid, which means if we want to get this thing back up to boiling again, we're going to have to increase the vapor pressure up to atmospheric pressure again. And as we saw on our previous slide, the way we can increase the vapor pressure of a solution is to, again, heat it up. But because the vapor pressure is now lower, it's going to require more heat to get enough molecules to enter into the gas phase. The net effect is, therefore, by dissolving a non-volatile solute into the solution, the boiling point of the solution has a tendency to increase. We call this the boiling point elevation due to the process of dissolving a non-volatile solute into the solution. Now, the question that people might tend to ask would be, when we're going through and making something like, say, spaghetti, one of the steps in the process of making spaghetti is to dissolve salt into water. And recall that upon dissolving salt into water, salt will dissociate into its non-volatile ions in the solution, that is, sodium ions and chloride ions. And the question we have is the reason why we dissolve salt into water because it increases the boiling point of the solution and therefore allows us to cook our food faster. Now, a couple things to think about here. Number one, the amount of salt you actually add into your solution is generally just a pinch of salt into your boiling water. And if that was the case, then the concentration of those dissolved ions should be relatively low, which would imply, therefore, the net change in the vapor pressure should be relatively low because very few of the spots at the surface of the liquid would be occupied, therefore, by sodium ions or chloride ions, and therefore it should have a minimal effect on the overall vapor pressure of our solution. If we just have a couple of ions here and there blocking the liquid water from escaping into the gas phase. So if the purpose of adding salt into the water were actually to increase the boiling point, then by logical thinking, we should probably try to make the solution as saturated as we possibly could in order to increase the boiling point by the largest possible amount, and therefore increase the rate at which our food cooks at a higher temperature. So if you did add a pinch of salt, yeah, maybe you might be able to increase the boiling point by a tiny, tiny, tiny fractional amount. But given that we're not saturating the solution, we should expect to see the actual boiling point increase by a very, very small incremental value. And therefore, the real reason we actually add that salt into the water is not because it allows it to boil at a higher temperature, but really because salt just tastes kind of awesome. All right, now the math behind how this works, this process of boiling point elevation, is described. What do I do? Now, as boiling points can be elevated by dissolving a non-volatile solute into the solution, as it turns out, there can also be an effect on the freezing point of the system as well. So let's look at this from a different perspective now. What happens to the freezing point of a solution when we dissolve a non-volatile solute into the solution? So thinking back way back to the beginning of first semester, we defined freezing point as being the temperature at which the solid and liquid phase species exist in equilibrium with one another. That is to say, the rate at freezing exactly equals the rate of melting at the freezing point of the solution. That is the position of equilibrium. Now, what's going to be the net effect of dissolving non-volatile solute particles into the solution on the freezing point of our system? Well, if we originally have a sample of ice water at a temperature of 0 degrees Celsius, that is the freezing point or melting point of water, the solid phase and the liquid phase would originally exist in equilibrium with one another. But if we dissolve salt particles into that solution, that is dissociated sodium ions or chloride ions, the sodium ions and chloride ions, again, are occupying portions of the solution that had originally been occupied by water molecules. And so if we kind of zoom in here again and look at the surface of one of those ice cubes here now in a particle picture, if we were to look at the surface of one of those ice cubes, at that surface, at the freezing point of water, the rate at which water molecules are, through their random molecular motion, reattaching to the surface and becoming part of the solid phase as they lose a little bit of kinetic energy in that collision, that rate is exactly balanced by the rate at which a solid phase water molecule melts into the liquid phase. That was, the system has now established equilibrium. And let's think about what happens now if we introduce those non-volatile salt particles into the solution here. So all of a sudden, we've got salt ions, sodium ions or chloride ions, occupying positions within the solution that had originally been occupied by those water molecules. The net effect of that is that some of the water molecules that were before going to be returning to the from the liquid phase to the solid phase are going to be blocked from freezing. Whereas water molecules can still melt into the liquid phase at the same rate as ever before, because the presence of the salt molecule doesn't block the escape, it really blocks the ability of water molecules to refix to the surface. And the effect of that is that the rate at which liquid phase water turns into solid phase water goes down, but the rate at which solid phase water changes to liquid phase water remains the same as it ever was before, which implies, therefore, a shift in equilibrium to the right. And because this shift in equilibrium has gone to the right, we're going to then reestablish equilibrium, that is, see the system here re-established into freezing point. We recognize that this is a endothermic reaction as written in the forward direction here. If we wanted to increase the rate of freezing, that would imply that we would either have to increase the rate, or we could really decrease the rate of the forward reaction, that is the solid changing to liquid, by lowering the temperature. And by lowering that temperature, we could therefore slow the rate of melting until the system has reestablished equilibrium. So the net effect of that would be to see that the freezing point of water should therefore be depressed, that is, decreased, because it requires a lower temperature in order to reestablish that equilibrium between the solid phase and the liquid phase. Now you see the effect of this in the real world when we look at something like, say, adding road salt to the roads to help keep the water on the liquid phase at lower temperatures during a snowstorm. So that's the qualitative understanding of how boiling points are elevated and freezing points are depressed by dissolving a solute into water. Now, with that in mind, let's next take a look at the math behind how this whole thing works. And these properties that we've described, that is boiling point elevation and freezing point depression, are what we refer to as colligative properties. These are properties which depend only upon the concentration of the solute in the solution, not the identity of the solute in the solution. That is, it doesn't matter what species we're dissolving, all that matters is how concentrated that solution actually is. And as it turns out, both boiling point elevation and freezing point depression are colligative properties that is, they are independent of the identity of the species in terms of the effect that they'll have on the solution. Now, we said that they are concentration dependent, and as it turns out, the concentration unit we need to talk about is an unfamiliar one to you. This is one we have not yet discussed. Another way of measuring the concentration in a solution is by what we refer to as the molality of the solution. Now please make sure you are careful to keep this separate in your mind from another idea we talked about already, which is the molarity of a solution. Molarity, that is a big capital M, if you might recall, is defined as the number of moles of solute solved per liter of solution. In contrast to that, a molality, which is a lowercase m, is defined similarly, but a little bit different here. It is the moles of solute dissolved per kilogram of solvent. And interestingly, because molality is defined as moles of solute per kilogram of solvent, molality is a unit of concentration, which does not change depending upon temperature. You saw in our lab that molarities can change depending upon temperature, because by changing the temperature, you actually affect the volume of the solution, and therefore the molarity. But because molality is the number of particles, that is moles per mass kilogram, and the particles nor mass are affected by changes in temperature, and therefore molality is a unit of concentration, which is independent of temperature. And the math behind how these two concepts works, that we've just discussed, is described by the equations given here in the center of the board. That is, a boiling point is elevated within a solution if we dissolve a non-volatile solute. Based upon the equation, the change in temperature from the standard boiling point is equal to a constant, we call Kb the boiling point constant, which is dependent upon the identity of the solvent which you are using to dissolve your solute. Another factor, which we'll discuss momentarily, called the Van Hoff factor here. That Van Hoff factor is given as the unit I. And then the molality of the solution. That is to say that there is a direct positive correlation between a change in temperature and a molality of the solution. So an increase in concentration will cause an increased elevation of the boiling point. Likewise, when calculating a freezing point depression, the equation looks almost the same. The big difference is now, rather than using the boiling point constant, again, which is solvent dependent, instead we use a freezing point constant as well, which really essentially tells you how large of a change in boiling point there is given the particular solvent you're actually using. Now, because in almost all instances in this class, the solvent you'll be using is water, we've given you here the boiling point and freezing point constants for water. Those being, for the boiling point, a temperature change of 0.51 degrees Celsius kilogram per mole, and for the freezing point constant, a change in temperature of 1.86 degrees Celsius kilogram per mole. Now, the one thing we haven't yet discussed there is that Van Hoff factor, I, given in either of these two equations here, for our boiling point and freezing point changes. The factor I, which we refer to as the Van Hoff factor, in essence is a factor which reflects the tendency of a solute to dissociate into different numbers of particles. Now, you might remember from our writing dissociation equations, seeing some information here about how these things split apart. If we take salt, table salt, and dissociate it into its component ions, one molecule of NaCl will dissociate into one positive sodium ion and one negative chloride ion, implying a single molecule of salt has dissociated into two distinct ions, which gives us, therefore, a Van Hoff factor of 2. And remember, in a colligative property here, the identity of the species which is in the solution doesn't really matter. All that matters is the concentration. So because sodium chloride breaks apart into more particles, regardless of whether those particles are sodium ions or chloride ions, they have the same net effect, that is to block water molecules from escaping from the liquid. So we say the Van Hoff factor of sodium chloride is 2, and contrasting that here, we could look at something like magnesium chloride, which dissolved into water, will separate into one magnesium ion and two chloride ions, yielding a Van Hoff factor of 3, for 3 total ions formed from the dissociation of one of these single particles. And likewise here, we might have something like, say, this is ferrous phosphate, Fe3PO42, which when dissociated forms 3 ferrous ions and 2 phosphate ions, yielding a total Van Hoff factor of 5 for the 5 total particles that form in the solution upon the dissociation of those species. Now, you notice by looking at the equations that the Van Hoff factor is directly proportional to the change in temperature we expect to see in either our boiling point or our freezing point. Which should make logical sense because the more particles that are present in the solution, the better the ability of those particles to block the escape of water molecules from the liquid phase into the gas phase if we're talking about boiling point elevation, or the better the ability of those particles to block the return of liquid phase molecules onto the surface of ice in the freezing point depression. So with those definitions and equations given here, let's go ahead and take a look at a couple of example problems that we can use using these concepts. So first example here is what happens if we took 33.8 grams of solid magnesium chloride, which is road salt, and dissolved that in 100 milliliters of water to the freezing point of our resulting solution. So we've got a couple of steps along the way here that we get to undertake here. Number one is to recognize that we're looking at a freezing point here, which means our equation we're using is a change in temperature from the standing center freezing point is equal to Van Hout factor I, the freezing point constant Kf, times the molality of the solution. First, we need to recognize that our species that we're using to form this solution is magnesium chloride, MgCO2. Let's go ahead and write the dissociation equation for magnesium chloride. Upon dissolving into solution, magnesium chloride forms magnesium ions in the aqueous solution, and not one, but two chloride ions. And therefore, we expect to see a Van Hout factor from this dissociation of 3, given the 3 total particles, 1 magnesium and 2 chloride ions that form from our solution. So we've got a Van Hout factor of 3. The next thing to recognize is that our Kf here is going to be dependent upon the solution of water here, and the Kf for water is equal to 1.86 degrees Celsius kilogram per mole in our solution. And that really leaves us with one big question here, which is what is the molality of that solution? Recall by our definition, molality was defined as being the moles of the solute per kilogram of the solvent. Now we've not been given moles, we have been given grams of magnesium chloride, which means we need to make a conversion from grams of chloride into moles of magnesium chloride. And we've also not been given a mass of solvent, we've been given a volume of water, which means we need to go from milliliters of water into our kilograms of water. Let's go ahead and do our grams to moles conversion first. And you have to pause for me for a moment here while I grab a calculator and calculate the molar mass of magnesium chloride. So, if we have a look here, if we had 33.8 grams of MgCl2. Making a quick calculation to go from grams to moles, I have to know that in magnesium chloride, MgCl2, we've got 1 magnesium, which has a mass of 24.3050 grams per mole. I have chlorines, 2 of those, times 35.4527 grams per mole. Add those values up here together, this gives me a molar mass of 95.2104 grams of MgCl2 per mole. You can take that value and plug it into our monorail. From the bottom, there are 95.2104 grams of MgCl2 per 1 mole of MgCl2. Making a division there, that gives me a value of 0.355 moles of MgCl2. So first step, so far so good. We now have our number of moles of magnesium chloride, which we needed in our molality calculation. Number 2, we need to know the kilograms of our solvent. And here we can set up yet another quick monorail. We recognize that we have 100.0 milliliters of our water. And this time, we recognize that our density of water is generally 1.0 gram of H2O, or close enough to it, per milliliter of solution. And then converting milliliters into, grams into kilograms, there are 1,000 grams in 1 kilogram. And making this calculation here will give me, not surprisingly, a mass of 0.10 kilograms of our water. And at this point, we can go ahead and plug in all of these values into our equation for the change in temperature. Our change in temperature from our standard boiling point was the Van Hoff factor, which we determined to be 3 times the freezing point of, freezing point constant for water, which is 1.86 degrees Celsius kilogram per mole, times the molality of the solution, which again was defined as moles per kilogram, which again was 0.355 moles of magnesium chloride dissolved in 0.10 kilograms of our water. Multiplying this value out gives me 3 times 1.86 times 0.355 divided by 0.1. A value of 19.8. Watching my units here. Moles cancel with moles, kilograms cancel with kilograms. This is the value of degrees Celsius. That is not my answer here, because remember, we are looking for the freezing point, not the freezing point depression. What we've just solved for is the change in temperature. So as we recognize that freezing points are depressed, that means that our actual new freezing point went from originally what it was at 0 degrees Celsius to a new depressed freezing point, 19.8 degrees Celsius, lower than it was before, which means our actual freezing point of the solution, therefore, is negative 19.8 degrees Celsius. All right, so there's one example here of how we can use our colligative properties in order to make a calculation. And this is a really important value we've just calculated here, because by dissolving road salt onto water, you'll see the net effect of that is to significantly lower the freezing point of our water well below the normal freezing point of 0 degrees Celsius, which allows those roads to have liquid phase water on them at lower temperatures and therefore get less slippery for cars driving on the surface. All right, now next we've got one more example problem we can do here. As it turns out, this last example problem is kind of a laboratory problem, which is really useful in terms of utilizing colligative properties in order to determine the identity of unknown species in solution. So this particular problem here is going to be a problem in which we are going to dissolve some unknown carbohydrate into a certain amount of water. And when we look at that solution, we're going to measure its new boiling point. And we want to use this information to calculate the molar mass of that carbohydrate. So let's go ahead and have a look here at our equation. We really only have one equation which deals with those colligative properties, which is the change in temperature. So our equation again here is delta T. In this case, is equal to the Van Hoff factor I times now the boiling point constant Kb, as we are now looking at the boiling point of the solution, times the molality of that solution. First thing we need to consider here is which of these values we currently have some information about. Number one, the species which we have is a carbohydrate which is dissolving. Recall from earlier in the year, we talked about carbohydrates being species which are made up of carbon, hydrogen, and oxygen, all three of which are non-metals and therefore tend to form covalent bonds between them, which means when this species dissociates when this species dissolves, rather than disassociating into ions, instead it should dissolve molecularly as unit molecules, which means for any non-ionic solute, we should expect to see a Van Hoff factor of 1. That is, it does not dissociate into ions, instead it dissolves molecularly. So we got our Van Hoff factor taken care of. We also happen to know that this is the solvent water, which implies there the boiling point constant Kb is a known value of 0.51 degrees Celsius kilogram per mole. And so really, looking at our equation here, we have information both about the Van Hoff factor and the Kb value, which means all we have to really look at, therefore, is the real change in temperature. Now be careful here. Van Hoff factor tries that it's not a boiling point, but a change in temperature from the standard boiling point. Because water's standard boiling point is 100 degrees Celsius, that means our delta T value is therefore equal to the difference between the observed boiling point and the standard of 100.34 degrees Celsius minus our standard boiling point of 100 degrees Celsius. And that therefore will give us a change in temperature of 0.34 degrees Celsius for our delta T. So looking at this equation, what we know is delta T, we know Van Hoff factor I, and we know Kb. The only thing we don't know is the molality. So let's go through now and rearrange this equation to solve for our molality. The molality of this solution, by definition, therefore, will be equal to our change in temperature delta T divided by Van Hoff factor I times the boiling point constant Kb, which will therefore be equal to, in this problem, a change in temperature of 0.34 degrees Celsius divided by our Van Hoff factor of 1, the boiling point constant, Kb, of 0.51 degrees Celsius kilograms per mole. Watching our units here, you'll notice that degrees Celsius cancel out, leaving me with 1 over kilograms over moles, which comes out as moles over kilograms. So all we need to do is divide 0.34 divided by 0.51, which gives us a molality equal to 0.67 units. There would be therefore moles per kilogram. So we have a 0.67 molal, or mole per kilogram, solution present here. Now once we know that molality, again, by definition, recall that molality is equal to the moles of solute divided by the kilograms of solvent. And looking at our solvent, we dissolve this in 150 grams of water, which means I just need a real quick conversion to get that into kilograms, and I can therefore rearrange and solve for my moles of solute in this particular equation. So rearranging and solving here, multiplying both sides by kilograms of solvent, I get the moles of my solute is therefore equal to the molality times the kilograms of the solvent, which we can now use some values from our calculations. Our molality was again 0.67 moles per kilogram times the kilograms of the solvent. 150 grams converted into kilograms is simply 0.1500 kilograms. And that would imply, therefore, the number of moles of solute which have been dissolved is 0.67 times 0.1500, which gets me 0.1005 moles of our solute, which is the unknown carbohydrate. And again, looking at this here, the question specifically asked me for the molar mass of this solute. So by definition, recall from earlier in the year, a molar mass is equal to the number of grams per mole of a substance. We've been given grams. That was, we had 18.00 grams of our solute divided by the number of moles, which was 0.1005 moles. And this gets me here a molar mass of, surprisingly, 18.00 divided by 0.1005, a molar mass of 179.1 grams per mole. watching our sig figs here, really should be recorded to two significant figures based upon our molality, which gives me a molar mass of 180 grams per mole of this substance. Which, interesting enough, happens to be the molar mass of a carbohydrate you all know and love, which is C6H12O6, whose molar mass is again 180 grams per mole. So that being said, we can look to a change in a colligative property, like boiling point elevation or freezing point depression, that will allow us to determine a molar mass of an unknown substance, which can be really, really useful in terms of identifying unknowns, particularly present in maybe a biochemistry setting where you're looking for the molar mass of an unknown protein. Use it as an identification tool. Right, and that is our discussion of colligative properties.